Hello everyone, this is the 50th lecture of the course Process Equipment Design, and in this lecture we are going to discuss the distillation column. Okay, so let us start this lecture. So as far as this lecture is concerned, we are covering the process design over here, and previously I have covered the distillation column and continuous process and previously I have covered distillation and continuous process, then design of binary system using McCabe-Thiele method, and then we also have discussed the multi-component system, and in this lecture we will further elaborate this topic. Okay. So, let us start this lecture. So, here we are going to discuss design of multi-component system, and before start the design of this we should consider light as well as heavy key component. So, what is basically light key and what is basically heavy key? If we consider the basic definition, light key is basically which has more volatility, okay, and heavy key which has less volatility, and that is very easy to choose when I am having two component. One would have larger volatility or higher volatility, we consider that as lighter component, other one will definitely be a heavier component. Okay. But how we have to choose this when I am having multi component system, that is important. So, to do that we follow some criteria, and that criteria is, so let us say I am having 4 component A, B, C and D in the feed, and we can arrange these component in the feed, top product and bottom product with respect to the volatility. Okay. So, highest component should be placed at top, and then we can keep on arranging the components which has light, and then we keep on arranging the component which has lower volatility, right. So, in this way we can arrange the component with respect to their volatility. Okay. So, how I can choose the light key and heavy key? The condition is like lightest component in bottom. Okay. Please listen it carefully. Lightest component in the bottom is represented by light key, and heaviest component in the top is represented as heavy key. Okay. So, with this definition, if I consider lightest component in bottom and that component is B. Okay. So, this is considered as the light key. Similarly, if I am having heaviest component in top is the heavy key, and which is basically this C component. So, this we consider as the heavy key. Okay. So, in this way we can consider B as the light key and C as the heavy key, and we will design the system based on the separation between B and C. Okay. I will not focus on A and B, okay, that will be separated along with these components only, but my main focus will be to separate B component from C. So, let us see how we can design the multi-component system, and for that we have the method like Hengstebeck's method. So, according to this method, for any component I, the Lewis-Sorel material balance equations and equilibrium relationship can be written in terms of individual component molar flow rate in place of component composition. Okay. So, what we can consider over here, that there are 2 points. First is we have to consider individual molar flow rate of each component. Okay. And second is at the place of composition I should consider molar flow rate, right. So, let us see the material balance changes with respect to this consideration. So, here I am having the balance at the top, and that is basically above feed. So, V n plus 1 should be equal to Ln plus D. This equation we already have seen previously, and equilibrium relation will be yi should be equal to Ki into Xi. So, Ki basically equilibrium constant, and when we consider this is And when we consider this in Hengstebeck's method, it is represented by small v. You can see here I am having total V, which is, here I am having capital V, which is nothing but the total flow rate. Okay. So, here for each component we can have a small v. So, small v n plus 1 I should be equal to L n I plus d I, where I is the ith component, right. So, in the similar line I can write this equilibrium relationship as small v n I divided by capital V. So, it will give the value of this, and that should be equal to k n I, and it should be multiplied with L n I divided by L. So, that will be this value. So, in the similar line we can consider equations in stripping section as L dash n plus 1 I, and dash you can understand this, and dash you can understand this is basically for stripping section. It should be equal to V n I dash plus B I, and similarly this is the equilibrium relationship. Okay. So, here we have different nomenclature which we have used, and these are basically L n I, which is the liquid flow rate of any component I from stage n. V n I, vapor flow rate of any component I from stage n, and d I is the ith component which is available in the distillate. Okay. B I is the ith component available in the bottom product. K n I equilibrium constant of component A, and here we can consider prime or dash to denote stripping section, that is the known fact. Capital V and capital L are the total flow rate that we consider as constant. Okay. So, in this way we consider different. So, in this way we consider Hengstebeck's method, where flow rate of each component is considered. Okay. Now, why it is considered so? When we consider Hengstebeck's method, it basically counts the fact, and that fact is basically when I am having heavy key as well as light key, right. So, obviously I will have some non-key component also, like light non-key and heavy non-keys. Okay. So, this method considers that flow rates of non-key components are constant. Okay, and that we consider as the limiting flow rates. Okay. So, if I consider the constant flow rate of non-key component, I already know the total flow rate, like capital V and capital L I already know. So, if I deduct the non-key component flow rates from the total, what I will get? I will get the flow rate of key components only. Okay. So, in that case what basically we are considering? We are considering that the multi-component system is now transposed to binary system, where I have only two component, the light component and heavy key component. Okay. So, that is the basic fact about the Hengstebeck's method, that it considers or it transposes multi-component system into binary system, and then we consider that as pseudo binary system, right. So, now I am having binary system only, so we can solve the same problem considering McCabe-Thiele method. Okay. So, Hengstebeck's method is basically pseudo binary system based method. Okay. So, let us see how we can proceed further with this method. So, to reduce the multi-component to the equivalent binary, it is necessary to estimate the flow rate of key components throughout the column. Okay. And to do that, Hengstebeck makes use of the fact that in a typical distillation, the flow rate of each light non-key component approaches a constant, which we consider as limiting flow rate, and that we consider as the limiting flow rate in rectifying section. In the similar line, flows of each heavy non-key component approach limiting flow rates in stripping section. Okay. So, this is the fact which we have already discussed, that it considered the flow rate of non-key component as constant, which we also consider as limiting flow rates. Okay. And further, Putting the flow rates of non-keys equal to these limiting rates in each section enables the combined flow rate of key components to be estimated. Okay. So, let us see how to do that. Here I am having the rectifying section and here we have the equation. So, LE and VE is basically the LE and VE are basically the flow rate of key components. Okay. And here we have summation Li and summation Vi, these are basically the limiting flow rates of non-key component, right. And if I consider and if I deduct these from the total flow rate, I can find out the flow rate of key component, and this we are considering in rectifying section only, and therefore, Li and Vi are basically considered for non-light key component. Okay. And similarly, here I am having summation Li dash and summation Vi dash, these will be for the components which are non-heavy key, okay, and these are the limiting flow rates. These we deduct from the total flow rate to find the flow rates of key components. Okay. So, as far as that LE, VE, LE dash, VE dash is concerned, these are the flow rates of combined keys as it is shown over here. So, Li and Vi are basically the limiting liquid and vapor rates of the component lighter than the keys in the rectifying section. Okay. And similarly, Li dash and Vi dash are limiting liquid and vapor rates of components heavier than the keys in stripping section. Okay. So, in this way we can represent the complete multi-component problem into binary system, and then we can now we can see how to find out limiting flow rates of non-key components. So, to do that, we have these equations where Li underscore and where Li underscore is equal to di by alpha I minus 1 and Vi underscore is basically Li underscore over here, and that should be added to di. So, this will be used over here. Similarly, for stripping section we can consider this, and this should be used over here. So, it is basically Vi dash underscore. Okay. So, this correction you can find. So, this correction you can consider, and we can have alpha I, which is the relative volatility of component I relative to the heavy key. Okay. And alpha Lk is basically relative volatility of light key relative to the heavy key. Okay. So, when we consider multi-component system, relative volatility we can always obtain based on heavy key. Okay. And now we will consider the Hengstebeck's method, as it estimates the flows of combined key which enable the operating lines to be drawn for equivalent binary system. Okay. So, for equilibrium line we can find out the relation as y is equal to alpha Lk x divided by 1 plus alpha Lk minus 1 into x. Okay. So, this we have already discussed. This is basically the relative volatility of light key with respect to heavy key. Okay. And y and x refer to the vapor and liquid concentration in light key. Okay. So, now once the problem is transposed into binary system, we can consider McCabe-Thiele method to find out number of trays for such system. Okay. So, that is basically the Hengstebeck's method. Now, we will illustrate this method with the help of some examples. So, let us say we have example 3. In this example, multi-component distillation column has following compositions with relative volatility. So, you see here I am having the component like C1, C2 to C5, and we can already have the light key as well as heavy key, and the composition is like feed, and the compositions of feed, top and bottom are given to us. Okay. So, if you consider this feed, total is basically 100, and here at the top it is 46 and at the bottom it is 54, right. And as far as volatilities are concerned, at top temperature and bottom temperature of distillation column, these are the volatilities. Okay. So, what we have to do? We have to use Hengstebeck's method to calculate slope of top and bottom operating line where reflux ratio is considered as 3. Okay. So, in this way we need to find out the top and bottom operating line slopes. Okay. So, let us start this using Hengstebeck's method. So, as far as that Hengstebeck's method is concerned, first of all we need to find out the average volatility. Okay. So, as far as average volatilities are concerned, these are basically relative volatilities, because if you see corresponding to heavy key we have value 1. Okay. So, all these volatilities at top and bottom temperature are relative volatility. So, we can simply make the geometric mean of that to find out average volatilities of different components. We can find out average relative volatilities of different components. Okay. So, that you can do, it is not difficult. And now we have to find out limiting flow rates of non-key. Now, if you consider C3 as a light key, so C1 and C2 are non-light keys. Okay. And if C4 is the heavy key, C5 will be non-heavy key. So, accordingly you can choose the limiting flow rates of limiting flow rate of non-key components. Okay. So, here if I am having C1 and C2, we can find out relative volatilities which are already available, and here we have the flow rate in distillate corresponding to C1 and C2. So, you can see here I am having 4 and 13. So, these values are given over here, and then we can have limiting flow rates of Li as well as Vi. So, that is basically the Li underscore and Vi underscore in usual expressions which we have discussed previously. So, simple calculation is there, you can find these values, and addition of this will give the summation Li and summation Vi. Okay. And in the similar line we can find out the limiting rates of non-heavy key, as C5 is the only component available in that category. So, we can find out alpha I for that, and Bi which is 30, which is given as 30 in the table, and here we have Vi dash, this is not 1. Okay. So, you consider all these as prime or dash. Okay. And here you can find out the Vi prime underscore as this, and then we can simply add 30 to this to find out this value. Okay. So, summation you can find like this. Okay. And now we have to find out flow rates of top operating line and bottom operating line, and that flow rate is L by V at top and L dash by V dash at the bottom, right. So, in that case we first consider the flow rate of key components, and how we do this? We know total flow rate, and from that we will deduct limiting flow rate of non-keys. Okay. So, here we have the flow of combined key. So, Le is basically the combined key flow rate in liquid phase. So, that should be 3 into 46. 46 is the total distillate and 3 is the reflux ratio. So, that is nothing but the L. Okay. So, you can see Le is basically L minus summation Li. Okay. So, that we can consider over here. This value we have already calculated. So, this is the value of Le. Similarly, VE, how we can consider? For that I need to know V, and that V should be equal to L plus D, right. So, we can consider 4 into D okay, and minus this factor. So, 159.083 we can obtain, V E dash we can obtain as V prime minus this factor. Okay. So, this will be nothing but equal to this only. So, that we can consider and deduct this value, okay, and so we can find V E prime as 161.653 and L E prime we can obtain as, and L E prime we can obtain considering this equation where L dash is basically V dash plus B. Okay. So, that B is 54 and V dash we already have computed over here. So, that we can consider here as well, and from this we will deduct this value, okay, and we can find the L E dash as 185.65, okay, and similarly we can simply calculate the slope of operating line like this, fine. So, here I am considering another example where Hengstebeck's method is used to again calculate the top and bottom operating line. Reflux ratio is 3, but here we have more number of components, okay, and in this case I am giving equilibrium constant at average temperature. So, how I can find the relative volatility? That should be K I by K heavy key. Okay. So, considering this we can simply find for this 2 by 4 divided by this, that is 0.6, that is 0.4, and that should be equal to 6. Okay. So, in this way you can find out relative volatility, and accordingly we can calculate relative volatility of other component, and we can simply find out all these values which are represented, which are shown in these tables, and L E, V E, V E dash, L E dash we can find as we have discussed in the previous example, and these are basically the slopes of operating lines at top and bottom. Okay. So, in this way we consider the Hengstebeck's method. Now, we can have another method to calculate number of trays in multi-component system, and that is Erbar-Maddox method. Okay. You can ask that in Hengstebeck's method we have not calculated number of trays. So, that you can obtain by considering McCabe-Thiele method once you have transposed the problem from multi-component to binary component. Okay. So, that is the repeated thing. So, I am not consider. So, that is basically the repeated exercise. So, I have not considered that. Okay. So, let us discuss Erbar-Maddox method now, and that is the empirical correlation based, and here we have this graph which is all about this method. Okay. If you consider x axis of this, that is Nm by N. Nm is basically minimum number of trays and N is the actual number of trays which you have to find. Okay. If you see here I am having different lines, and these lines correspond to Rm by Rm plus 1, and that Rm is basically minimum reflux ratio, right. So, that we can consider in these lines, and on y axis we have R by R plus 1. So, that is the actual reflux ratio given in the problem. So, basically you know this and you can also calculate this. So, depending upon all these value you can find the Nm by N, Nm number of trays you can also calculate, and so you can find out N number of trays, that is the actual number of trays for the given separation. Okay. I hope method is clear. Now, we will see the value of different terms. First of all, we will find the value of Nm, that is the minimum number of trays, and that we can obtain at total reflux condition. Okay. So, for minimum number of trays calculation we can find. So, for minimum number of stages calculation we can consider Fenski's equation, okay, as you can see over here. So, this is the Fenski's equation where xi by xr is the ratio of concentration of any component I to the concentration of a reference component R, and the suffix D and B denotes distillate as well as bottom, right. So, here I am having Nm as minimum number of stages alpha I is the average relative volatility of the component I with respect to reference component, and reference component is usually the heavy component. So, when we resolve this, we can find this expression to find out minimum number of strays based on light key as well as heavy key. So, here also we can consider the selection. So, here also we should consider selection of key component first, and based on that we can use this, equation, right. So, once I am having Nm value, we can find minimum reflux value, okay. We can find minimum reflux ratio value, and that we can obtain through Underwood's equation, and Underwood's equation is given as where summation alpha I x I d by alpha I minus theta should be equal to Rm plus 1. So, this Rm is basically minimum reflux ratio, okay. Alpha I is the relative volatility of component I with respect to reference component, and that is usually the heavy key. Fine. Rm minimum reflux ratio, that we have already discussed. XID is the ith component in distillate, okay. And how we can compute theta? So, for this we can have another equation which depends on the feed composition of ith component, and we can also consider Q line over here, okay. So, based on that we can find the theta value which can be obtained by trial and error method. So, how I can choose the correct value of theta? The correct value of theta must lie between the values of relative volatilities of light and heavy key. So, in this case you may have number of values of theta. So, wherever the value will lie between relative volatility of light key and heavy key, that value you can consider for theta, okay. So, this is basically Erbar-Maddox method, and quickly we will cover the example related to that. So, in this case we can have the same example which we have discussed as example 3 for Hengstebeck's method. So, all these points you know already, and here we have to compute number of trays using Erbar-Maddox method. So, feed is at boiling point where Q should be 1, right. We have to consider reflux ratio as 3. So, let us start that. So, here we have relative volatility with respect to heavy key at top as well as bottom, and average of that we can already, we have already calculated in previous examples that you can refer, okay. So, these values are already available to you, and we consider, and now we consider Erbar-Maddox method, and first of all we will find number of trays used, and first of all we will find minimum number of trays, that is Nm, and this is the expression. So, you can see we have to focus on this condition, right. So, X Lk in distillate. So, this is basically 28, and that is heavy key in distillate. So, that should be 1. So, that you can consider over here. Lk at bottom, that is basically 2 divided by 19. So, here you can consider this is basically H and this is L. So, this correction you should consider, and here if you consider heavy key in bottom, so that should be 19, and light key in bottom as 2. So, that you can consider as 19 by 2, and that should be divisible by alpha Lk. So, that is nothing but this value, okay. So, you can find Nm as 8.7176, and this is the and this equation we can use to find out theta value, and in this equation this XIF is basically the fraction of component I in feed, okay. So, if you see the total feed is basically 100, so that we can consider 1 by 100 over here, and then we keep on expanding this, and then we keep on expanding this expression. So, that should be alpha I. So, for first component 4.743 into 5, that is given over here, divide by this alpha I minus theta, okay, plus second component, this is alpha I, okay, and this is the xi, and again alpha I we can consider, and so we keep on adding this for 5 different components, and that will be equal to 1 minus q, where q will be equal to 1. So, that we can consider as 0. Okay. So, when we solve this, we can find theta value as 1.274. We can obtain more values also, but we should choose the value which will fall between relative volatility of light key as well as heavy key, as you can consider this value. So, in this way we can find out theta value, and further we have to find out minimum reflux ratio using Underwood's equation. Okay. So, this is the Underwood's equation. Solving this equation, because all components you know, here we can have Rm value as 1.39645. I think you can solve this very easily, there is no problem. So, once I am having Rm value, we can find out Rm by Rm plus 1, and reflux ratio in the problem is given as 3. So, we can find R by R plus 1. Okay. And now we can use the graph. You can see Rm by Rm plus 1 is 0.58 and this is 0.75, right. So, this is the graph where Rm by Rm plus 1 is 0.58. So, that should be almost 0.6, right. So, this is the curve, okay, and 0.75 is R by R plus 1. So, that you can consider this line. Okay. So, wherever it will cut this line, we can find Nm by N using this point. Okay. So, accordingly Nm by N you can find as 0.74, and so the number of stages N you can find as 11.78. So, that should be equal to 12 stages. So, in this way Erbar-Maddox method works, and so we will cover the second example of Erbar-Maddox method quickly, and that is this example, okay, where this is basically the light key and this is the heavy key, okay, based on the simple definition of it, and we can find the number of trays and we can find minimum number of trays using Fenski's equation. So, this you please change to this, okay, and the Nm we can find as 3.54, Q value should be 1. So, we can find the theta value also. So, this is another method to find out theta value. Either you can simply calculate that from the calculator by putting the whole equation, or you can simply keep on assuming the theta value and keep on calculating this till you will find the value should be equal to this, and that should be 0, right. So, this is almost 0. So, we can choose theta value as 1.118, and after that we can find out Rm by this calculation. So, that Rm is 0.3328, then Rm by Rm plus 1 we can find, R by R plus 1 we can find, and so the number of the number of trays we can find using the graph which we have discussed in previous example. So, total number of trays we can find as 6. And here I am having some of the references about this, and this is the summary of the video, and this is the summary of last 3 lectures of distillation column. Okay. And summary goes as: distillation process is discussed in detail, reflux ratio, that is total reflux, minimum reflux and optimum reflux is described, design method for binary system is discussed, design method of multi-component system is discussed, and we also have discussed Hengstebeck's as well as Erbar-Maddox method. And that is all for now. Thank you.